Hi Year 13s. We're going to look at area underneath curves, and to illustrate this principle we're going to go through this example here, which is asking us the area between this equation and between the two lines y equals 1 and x equals 3. So I've just completed the square on that so that it makes it easier for me to graph, and I'm not graphing it to scale, but my graph will look something like this. Okay. And then the lines x equal 1 and x equals 3, we'll just put them in like that. So we're being asked to look for the area between this curve and the x-axis and between those two lines. So x equals 1, x equals 3, and y equals x squared plus 4x minus 2. Now, because the area under that curve is curved, we can't work it out just by looking at the graph. And so this is where the application of the definite integral comes into play. And so if we integrate that function from the interval x equals 1 to x equals 3, that that integral actually gives us the area under the curve between those bounds. And so that would be the integral of x to the 3 over 3 plus 2x squared minus 2x, evaluated from 1 to 3. So substituting in those numbers, 3 cubed over 3 plus 2x plus 2 times 3 squared minus 2 times 3, and all of that minus those values, so minus 1 cubed over 3 plus 2 times 1 squared minus 2 times 1. Okay, so we'll put that into a calculator, see what we get out. So we have 3 to the power of 3 divided by 3 plus 2 times 3 squared minus 2 times 3. Okay, so 21 minus 1 over 3 plus 2 minus 2. So that comes out as 20 2/3. Okay, so once again we can check this by using the integral function on our calculator. And so we go option, calculus, integral, and we put in that first function, x squared plus 4x minus 2, and go from 1 to 3. And that gives us the same answer, so we know we are correct. Okay, so that's a summary of the whole purpose for doing definite integrals, to get that area under a curve. And it works when you have straight line x bounds, such as we have here. Okay.